In this video, we're going to look at how to create a shear and moment diagram when you have a distributed load. So again, we have the reaction forces given to us. In this case, we have a uniformly distributed load across the entire length of the beam. It's 5 kips per foot spread out over 20 feet. So that's 100 kips. So it's evenly supported by each support. Again, the strategy to employ here is to create the shear diagram directly below the beam diagram. And again, we're going to start with a horizontal line that represents 0 shear. At the beginning, we start off immediately. The first load that we encounter is a 50 kip load. So from 0, we immediately shoot up to a value of 50. Now, unlike in the previous example where we traveled along the beam and didn't encounter any loads, when you have a distributed load, you're constantly encountering load. This distributed load is just going to keep pushing us down, down, down. So while we may start off with a value of 50, that value is just going to decrease, decrease, decrease until we hit a value of 0, and it's going to continue to decrease, 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 decrease. And by the time it gets to the end, we will have been pushed down by this load of 5 kips times 20 feet, or 100. So 50 minus 100 gives us negative 50. But when we reach the end of the beam, we encounter a positive 50 kip load. So that's going to take the shear, excuse me, the shear diagram back up to a value of 0. And that's good. We want to end at 0 and begin at 0. So in this case, it's fairly easy to figure out where we cross the x-axis because it's going to be exactly in the middle of the beam. But if this distributed load hadn't gone all the way across the beam and it crossed the 0 axis at some point and we needed to find out where, we could simply do that by taking the maximum shear value here of 50, and that's 50 kips. I should label these units, 50 kips, divided by the rate at which we are losing our force, or at which the rate at which the shear force is pushing down on us, that externally applied load of 5 kips per foot. So when we take 50 kips divided by 5 kips per foot, that gives us a distance of 10 feet. So I know that 10 feet from the left support is where we cross the x-axis. So all throughout here, we are experiencing positive shear. Then we hit that 0 axis, and from midspan of the beam to the right, we are experiencing negative shear. And it ends at a value of negative 50, and then jumps back up to 0. So we need to use that shear diagram to now make a moment diagram. And again, we want to make that diagram directly below the previous one. So this is moment. And we'll start off with a horizontal line representing the value of 0. Again, we have a simply supported beam, so we're not resisting any moment at either end. Since we can't resist moment, that must mean that the moment is 0. Just like in the previous example, we need to keep in mind the relationship that the value of the shear diagram equals the slope of the moment diagram. But unlike in the previous example, our shear value is not staying constant. It is changing. It is starting off high and reducing, which means that the slope of our moment diagram is going to start high, like a rocket ship taking off, and as it travels along that beam, that slope is going to get less and less and less until right here at mid-span, the slope is actually going to be 0. So it's a tangent line drawn to that curve would be horizontal. And then the slope becomes negative. It's not extremely negative at first, just a little bit, but it's going to start getting a little bit more negative a little bit more, and a little bit more, until we get to the end where we're going downhill fast. We have a slope of -50 at the very end. So the moment diagram looks like this. We're starting at 0, increasing. The rate at which it increases slows down until we reach a maximum value at midspan. And so we have positive moment throughout this beam with a maximum value here at midspan. How do we determine the value of that maximum moment? Well, it comes from the area of the shear diagram. If I find the area of this triangle, the area is equal to 1/2 base times height. So the maximum moment in this case is going to equal 1/2 times the base is 10 feet wide, and the height of that triangle is 50 kips. So that would be 250 kip feet. So the maximum moment value is 250 kip feet. Okay, so the main points again that we want to be concerned with are the beginning and end values, anywhere where we cross over the y-axis, anywhere where we have a point load applied, and and anywhere where we experience a maximum moment. So these diagrams tell us that we begin with positive 50 kip shear. At midspan, shear is 0. At the right support, shear is -50. In regards to moment, we begin with 0 moment. We experience a maximum moment in the center of the beam of 250 kip feet, and then that reduces back down again to a value of 0 at the right support. So these diagrams tell us the shear moment values across the entire length of the beam. So that's how to make shear and moment diagrams. I may look at one more example that combines point loads and distributed loads in the next video.